All right, so as I mentioned, we are in kind of just the closing stages here of chapter 16. And really, there's only a couple of concepts to talk about, and they largely fit into the kind of the quantitative arm of how we are able to do qualitative analyses like what we've been doing in the laboratory. So we're going to start today by talking about complexes and how we can use complexes to dissolve solids. And these kinds of problems generally stem from just kind of what would it take? And so it's a combination of some equilibrium concepts that we started off with in chapter 14, where you can combine a couple of equations together to get a new equation and a new equilibrium constant by multiplying the equilibrium constants of however many steps there are, as well as looking at the formation constant and KSP. So the question I want us to consider is this: how many moles of potassium thiosulfate do we need to add to a liter of water in which 0.02 moles of silver chloride is suspended, that is undissolved, in order to dissolve the precipitate? Now, the complex in question here is the silver thiosulfate complex. And often what you'll see with complexes is, because we've got multiple sets of parentheses, you'll usually see it bracketed with the total charge on the outside, which would be -3 in this case. -3 because silver is +1 and each thiosulfate's -2. So there are two components to this problem. First of all, we've got the introduction of a new equilibrium system. Because what we are trying to do is we are trying to force the dissolving of this ion into a system that otherwise wouldn't want to be dissolved. So we've got the solubility product constant here. That is the equilibrium constant associated with the dissolving or not dissolving of the silver chloride. And then you've got the complex formation constant, Kf, that shows the very high affinity for forming this silver thiosulfate complex. And if you remember from earlier on in our equilibrium unit, we know that when we can add together two equations, the K values multiply together to give us the K value for the blended equation. So 1.8 times 10 to the -10th multiplied by 2.9 times 10 to the 13th, we get a equilibrium constant of 5,200. Calculator says 5,220. We have to round to 2 sig figs, so 5,200 will be the result. So as you can see, this is a very, very product favored equilibrium. And so that's why if we were to expose silver chloride to enough thiosulfate, we would anticipate, okay, it's gonna convert. Now, the other thing that we want to be mindful of, this is still a solid, and everything else is an ion, so it has to be aqueous. So our value of K is going to be equal to the concentration of the silver thiosulfate complex multiplied by the concentration of the chloride ion divided by the concentration of the thiosulfate ion quantity squared. So when it comes to answering the original question, how much thiosulfate do we need? It comes down to two pieces, basically. First of all, we've got to satisfy the stoichiometry. So if I have 0.02 moles of silver in the form of silver chloride, I'm going to need at least 0.04 moles of thiosulfate because I need twice as much just to make the complexes. And then we also need to consider how much excess thiosulfate there is to make the equilibrium go. And so for that, we would come back to this. And we would just have to do a little bit of manipulation. So if I have 0.02 moles of silver chloride, remember, this is going to turn into the complex. In one area and the chloride ion in the other in a one-to-one kind of fashion. So these concentrations we would know based upon the amount of silver chloride there was. The only thing we wouldn't know is the value of thiosulfate. We've got a liter of water, so that makes it nice and easy. K, which was equal to 5,200, is equal to 0.0200 molar for the complex, 0.0200 molar for the chloride over the concentration of the thiosulfate squared. algebraically, flip-flop the 5200 and the thiosulfate concentration, and I get 0.02 squared divided by 5200. The concentration of the thiosulfate squared is equal to 7.7 times 10 to the negative 8th molar. Square root of that is 2.8 times 10 to the negative 4th molar, which, since this is a 1 liter solution, would be 2.8 times 10 to the negative 4th moles. And so in terms of how much potassium thiosulfate do I need to add? It'd be the 0.04 plus 2.8 times 10 to the negative 4th. Which, rounding to the correct number of sig figs, would be 0.0403 moles in total. So that would be the number of moles of thiosulfate. From here, it would just be a matter of converting that moles into grams if that's what was asked of us. So if we get spotted with a question like this, where it asks us how many grams of how much ammonia does it take to complex zinc from zinc hydroxide? How much ammonia does it take to complex copper out of copper 2 sulfide using ammonia? This is the approach that you would take. Solve the stoichiometry first, figure out how much you have to add just to make the complex, and then use the combined equations to figure out the value of K, figure out how much extra you need just to hold the equilibrium to that product favored side. That's all it is. Right. Any questions with this one? All right. The last concept from a solubility standpoint that we want to talk about is amphitherism. Now, we've talked about substances being amphiprotic, could act as acid or act as base depending upon the circumstances. Amphitherism is a similar kind of phenomenon. Here we are looking at metal oxides and hydroxides that can be soluble in strong acid or in strong base. And really what's happening in either one is, in the formation of acid, what we'll see in those circumstances is just a simple acid-base reaction. In the strong base, we will see the formation of a complex. Now, this particular example of aluminum is one that you just finished with yesterday. This was the very phenomenon that you were doing to separate aluminum along with the chromium and the zinc from the other group 3 cations in the first place. Heavy dose of base, the ones that don't complex with hydroxide get pushed to the side, they stay a solid. The ones that do complex get separated, and here they are. And then one of the first steps in that subsequent evaluation was to reacidify the solution, get it out of the complex form, and then we gently brought it along to bring out that hydroxide with the aluminon indicator on it to prove the presence of aluminum. So aluminum and zinc are both common examples of substances that exhibit amphitherism. Zinc is especially good at it because not only does it complex with hydroxide, it also complexes with ammonia, which gives it another added kind of dimension. And that's actually one of the things that we use to separate it from the aluminum, because the aluminum doesn't complex as well with the ammonia. Tin also does it, but we haven't done any studies of tin other than to use tin as a reducing agent. Now, another thing that is related to a lot that we've been talking about is this idea of Q versus K. Now, we haven't really explored Q since chapter 14, when we were looking at, okay, I've got this system that is reversible. Is it at equilibrium? Which way is it going to shift? Well, we can use this same kind of idea of a reaction quotient to figure out if we've got enough substance present to actually form a precipitate. And so the process that we use is very simple. Calculate where we are, compare it to the KSP. If the Q value is bigger, we know it's going to precipitate. That is over the saturation limit. And if Q is less than KSP, well, that actually means that we are under the saturation limit. Everything's going to dissolve. It is with this kind of framework that we can actually start to use to separate those ions from each other. This is called selective precipitation. So take, for example, the difference between calcium hydroxide and magnesium hydroxide. Calcium hydroxide we consider to be a strong base. However, we know that its solid is not the greatest at dissolving in water. It dissolves. When it dissolves, it gives a really robust pH. But it's not always easy to get that stuff into solution. And with its KSP value at 5.5 times 10 to the negative 6th, there's a good reason why. But magnesium hydroxide is actually even worse. And so if I have the two in solution together, so here I've got a solution of 0.1 molar calcium ion and 0.02 molar magnesium ion. What I can look at here is I can do some math and I can figure out, okay, the concentration of hydroxide has to be 6.9 times 10 to the negative third molar for the calcium to start to precipitate. Where did I get that value from? Well, mainly I got it from just that application of, solving the ice table here. Because this magnesium hydroxide is so much less soluble, it's actually not going to take very much hydroxide to start precipitating it. And so the magnesium is going to precipitate first and precipitate and precipitate and precipitate. And then eventually we'll hit a point where there is enough hydroxide present that it'll start to precipitate the calcium as well. And we can actually figure out what the concentration of the magnesium would be at that point as well. And it would be 1.2 times 10 to the negative 7th, which is 6/10,000ths of a percent of the original concentration. So practically zero. We wouldn't say zero, but practically zero. So this kind of idea of selective precipitation can be used in very strategic kinds of ways. So again, just to kind of recap that relationship between Q and K. If Q is positive, if Q and K are equal, we're at equilibrium. And so we're going to see a natural saturated solution, a natural transition and interplay between the solid and the solution. If Q is less than K, we are at an unsaturated phase. We're going to see the addition of more dissolving until we get to that K value. If Q is bigger, we're going to see precipitation until Q and K equal out again. And selective precipitation is going to be kind of the means by which we utilize this. And the most common example of that, we'll come back to these in a second, is in qualitative analysis. So we just finished our third qualitative analysis experiment. Now, a couple of you still have a couple of steps left to do. We'll get to that this afternoon. But if you recognize the scheme here, this is what we've been following. And so if you started with just a general sample of a whole bunch of ions, the first things that you would remove would be the insoluble chlorides. We know those as the group 1 cations: silver, mercury 1, lead 2. The next thing that you would remove are the acid-insoluble sulfides. This is the process you would use using thioacetamide and peroxide and an acidic solution. You get copper, bismuth, cadmium, lead 2, mercury 2, arsenic, antimony, and tin. Now, in our group 2 analysis, we cut half of those out. Some of them for safety reasons, the cadmium and the arsenic being toxic as they are, or having toxic steps to get to them. I talked to you a little bit about the cyanide that you have to use to separate cadmium and copper from each other. Antimony and tin we cut for time. It lengthens the analysis by a day and results aren't usually all that good. And then you just finished the base-insoluble sulfides: aluminum, chromium, iron 3, zinc, nickel, cobalt, manganese, and we covered all those. Now, there are other analyses that you can do. We have skipped them, again, primarily for time. This isn't a qualitative analysis class. We're just kind of introducing you to the technique, and it does fold into what we've been talking about here. But if you were to continue on, your group 2 ions precipitate in a solution of phosphates. And then your alkali metal ions have specific flame tests to kind of tell them apart. And this hopefully looks a little bit familiar as well. If you've been reading through your lab archives, we've been giving you flow charts similar to these each step of the way. So that's kind of the big picture. That's where we were going, what we were looking at. Let's close off this chapter with a couple of example problems here. Just with this idea of will a precipitate form? So we've got lead 2 chloride, which was used as white pigment in sculptures. Will lead chloride precipitate when a 275 milliliter solution of 0.134 molar lead 2 nitrate is added to 125 milliliters of 0.0339 molar sodium chloride? The KSP for lead 2 chloride, 1.70 times 10 to the negative fifth. You'll notice that value for KSP is kind of on the high side. That's one of the reasons why we can use hot water to dissolve lead chloride, because raise that up high enough in temperature, it'll dissolve. So what we're looking at is the equilibrium between lead 2 chloride and its ions, the lead 2 ion and the chloride ions. Now, we don't need to do an ice table here because we're not trying to figure out the equilibrium concentrations. All we're trying to figure out is, are we at equilibrium? Now, the problem is, by combining these two solutions together, they've diluted each other. So I can't just put in 0.134 for the lead, 0.0339 for the chloride, and assume that that's good. I need to do the dilution equation first. So the total volume, 275 plus 125, would be 400 milliliters. So for the lead, it's 275 times 0.134 molar over 400. So its initial concentration is 0.0921. And for the chloride, it's 125 multiplied by 0.0339 over 400. So that's 0.0106 molar. Our Q value would be equal to the concentration of the lead ion multiplied by the concentration of the chloride ion squared. So that would be 0.0921 multiplied by 0.0106 squared. We get 1.03 times 10 to the negative fifth as our value of Q. So it's close, but we can see that Q is less than K. So we're not going to get a precipitate here. All right. Any questions with this example? Okay. So remember, we're combining two solutions together. So it would be the total volume of the both solutions together. So 275 from the one and 125 from the other. That'll give you your 400. All right, other questions? All right, last example. A solution contains 1 times 10 to the negative second molar silver, 2 times 10 to the negative second molar lead, 2. When chloride is added, both silver chloride and lead 2 chloride can precipitate. What concentration of chloride is necessary to precipitate each salt? Which one precipitates first? Okay, so this goes back to a couple of things. First of all, we've got to do the similar kind of calculation. Second thing is it is natural to assume that because the KSP value for the lead is bigger, that it's the more soluble salt. But we have to remember that we cannot compare KSP values directly. This is something we talked about yesterday. We have to look at molar solubility instead. So what we're really looking at here is I've got silver chloride and the KSP is equal to 1.8 times 10 to the negative 10th. If my initial concentration is 0.01, now, chances are pretty good that this is a 5% candidate. We could certainly check and be sure. We could also solve the quadratic, but as I mentioned in yesterday's class, the easiest way for these to check is if you solve it, applying the 5% approximation, and the value ends up adding significantly to the initial concentration, you got to rewind it and go back to the quadratic. In this case, if we ignore it, 0.010x, we'll get 1.8 times 10 to the negative 8th molar as X. And so that's the concentration of chloride that we would need for the silver. (1.8 times 10 to the negative 8th). For the lead, similar kind of idea, but we do have to keep in mind that there are 2 chlorides, and this is why we can't just simply judge it by the KSP values. So if we start with 0.02 molar lead, our KSP value is 1.7 times 10 to the negative 5th. It's equal to 0.02 plus x multiplied by 2x squared. Again, we're gonna ignore that term there. .02 times 4 is 0.08 x squared. 1.7 times 10 to the negative 5th divided by 0.08 is 2.1 times 10 to the negative 4th. Oh, got ahead of myself there. (2.1 times 10 negative 4th is equal to x squared. Square root of that, we get an x value of 0.01. And so this would tell us, hold on a second, that's practically just as much as what our initial concentration of lead was. So we would have to go back to solving this as a quadratic. So take all of that off the board. So that's why we do that. We do that because we know the 5% is a really fast trick. But if we recognize that, ooh, we need to go back to this, it's out of our league, we can quickly make that adjustment. So this is 0.02 plus x times 4x squared. So 1.7 times 10 to the negative fifth is equal to 0.08 x squared plus 4x cubed. Go to your favorite calculator solver. In this case, our cubic is 4. Our x squared term is 0.08. Our x term is 0. And our d term is negative 0.000175 or 17, sorry. So if we calculate that, once again, one of the numbers is going to make sense. The other two are going to be nonsensical, or in this case, imaginary. So 0.012 is the value that we would want for x. So very clearly here, the silver is going to precipitate first. Very, very clearly here. Which is why, if you remember when we did this experiment, why were we adding 6 molar hydrochloric? We needed a good bit of chloride ion presence to make sure that we got out all of these ions. All right, any questions here? All right, that wraps up this chapter. Let's go ahead and take our 10-minute break, and we'll come back and we'll do some review.